Hi, I'm Atul and I am in London right now.
Hi, I'm Paul and I'm in Burnley, Lancashire right now. Okay, so today we're going to look at calculating the pH of an acidic buffer solution. Now, an acidic buffer solution consists of a weak acid and its conjugate base, a weak acid and its salt, and here we're creating that by reacting a weak acid and a strong base. Because a weak acid and a base will give us a salt and water. So if we have a look at that reaction, we have ethanoic acid reacting with our strong base, sodium hydroxide. To give our conjugate base, or salt, sodium ethanoate, and water. So we need to work out how much ethanoic acid and how much sodium ethanoate we have at the end of this reaction. So we'll use the ICE method, which we've seen for calculating equilibrium constants, but here we're not calculating what we've got at the equilibrium, we're calculating what we've got at the end of the reaction. And all this will be in moles. So we want the initial moles of ethanoic acid, which is concentration times volume. Concentration is 1 and volume in decimeters cubed will be 0.025. So that gives us 0.025 moles of ethanoic acid. And for our sodium hydroxide, concentration is 0.4 times by the same volume, 0.025. And that gives us a number of moles of 0.01. Okay, and we've got nothing of the salt initially. So the sodium hydroxide is purposefully the limiting reagent. It's always less than the ethanoic acid to create the buffer solution. And so the amount of moles that reacts here is the sodium hydroxide moles, which is 0.1. And it's all a 1:1:1 ratio in the equation. So the change is 0.01. So what have we got at the end? Well, this ethanoic acid has gone down by 0.01, which leaves us with 0.015 moles. We've got nothing left of the strong base, and we've got 0.01 moles of sodium ethanoate. And so if we write our equation for calculating H plus for buffer solutions. So H plus is Ka times HA over A minus, or weak acid over salt. And they're in concentrations, and our calculations in moles. So when we write this, Ka is 1.74 times 10 to the minus 5. And we can just use the volume for the concentration. So for ethanoic acid, we've got 0.015 over the volume. And for sodium ethanoate, we've got 0.01 over the volume. And that shows why we can just use volume, because it cancels out. And then that gives us 2.61 times 10 to the minus 5 for the concentration of H plus, and therefore pH is minus the log of that. Which gives us 4.58. which is what we'd expect for an acid buffer solution pH.
Great. Yeah, that sounds good. So, I mean, as expected originally, you were going to get something acidic. So that confirms again that's just very slightly acidic, and it's expected.
Yeah, which is what we'd expect for a weak acid buffer solution, a weak acid pH.
And also, just going to point here a little bit on my cursor. So presumably, you could have used the actual value of the volume. You could have just worked it out instead of cancelling it.
We'd use the total volume there, so 50 centimeters cubed, which would be 0.05 decimeters cubed. We could have put in there 0.05, 0.05, but then again, they would cancel.
Right. And just to remind, from what I remember, a buffer solution is something that is resistant to small changes in pH. It's quite a useful solution to have.
Yeah, if we added a small amount of acid or alkali to this solution, then we'd expect the pH to stay around 4.58, say move to 4.6 or 4.56. And we can do calculations showing that maybe next time.
Great. No, sounds good. Yeah, so that's a really good one. Look forward to your next video, whenever that is.
Okay. Thanks, Atul.
Great. Bye for now.
Bye.